Hello everyone, welcome back to Business Intelligence. For the past week, I'm sure you all went through a lot. And I'm also sure that you have been doing better. I can see that from your exam. I can see that from the questions that I got from you. And, this is what I expected. Our routines had to be changed because of the COVID-19 pandemic, and we experienced the shock. Everybody experienced the shock. We can't do things as normally how we did, and we had to adjust. We had to work from home. We have different kinds of distractions. Some of you have kids. Some other of you have roommates. You have to share the same space where they may not be quiet when you need it to be quiet. Even though we don't have to travel and we save those time we normally spend on the road. We have more times. But working from home is not exactly very easy. It's not straightforward. It's complicated. But after all, we adapt. Your routines are adapted. You follow the same thing again. You design the routine. You make the routine work in a new environment. You repeat the routine over and over for the same objective of being, productive and trying to increase the productivity. And now, after a week of practice, things get better. And so did mine. I'm glad that it's working better. I'm also glad that everybody is sheltered at home, is reducing time of going out to try to constrain the spread of the virus. I hope this will go over very soon. It may not be so soon, but we should have faith. So everybody can do better, and trust me, because you know what? You're strong. Everybody, we are strong. We're at UH, and we all can do this. Here is our tasks today. First, I'm gonna have a few comments about exam 1, and I'll talk a little bit about the big picture of data mining, particularly about supervised models. And we'll talk about the main topic of this week, model evaluation. I'll introduce several new concepts and use some examples to illustrate those points. And in homework, you'll practice with these concepts on a specific problem. And after that, I'll mention an informal evaluation form that I will send out to you to get some feedback, especially under this COVID-19 emergency situation. The course structure has been changed quite a lot ever since the outbreak, and ever since that we have transitioned to work from home mode and asynchronous videos. So I have some specific questions to ask you for your feedback, and please provide your feedback. It will be very helpful for me to understand how you think about this course. And after that, I will finish today's video lecture with a small section about model implementation or model deployment in SAS Enterprise Miner environment. I'll do a few demonstrations on how to do those and highlight a few key points or things to modify from the PDF tutorials. Now, I have gone halfway finished exam 1. I thought everybody did excellent. I know that you guys are strong. I know you are intelligent. And even under a different way of studying and working, even with possible distractions and change of routines and everything difficult, all of you did so far that I have graded. All of you did excellent in exam 1, and I like to congratulate every one of you how well you did. Homework exam 1 is about the fundamental concepts that we have talked about in this course, including you have gone through the exam. What it was about: missing values, overfitting supervised versus unsupervised models, and supervised methods, data mining tasks. All of those are very fundamental, and the fact that you're doing well means that you are ready. You are very much ready for the second part of the course. You are ready to do the project, and even under an individual working mode, usually the final project are done through teams, but with this difficult environment we can't effectively do it, and it probably will cost a lot of time to coordinate the team. So I thought individual project might be feasible. Knowing that you all did excellent in exam 1 gives me faith that you will also do well in the final project. It won't be without difficulties, but I know that you will go through them by reflecting back on what you learned and on the fundamental principles of data mining and supervised learning projects. I know you can do it. All right, next I'm going to talk about the big picture of supervised models. So far, here are the models of supervised learning that you have learned, except for the last one. So let me change the color. This time I'm going to use some green colors, except for this one. So we haven't learned deep learning, and we will not learn deep neural network models, which is part of the deep learning models that is very popular nowadays in data science because of their capability. But we have learned linear models, and an example would be regression models, including simple linear regression and multiple linear regression. And even though logistic regression is not exactly linear model per se, but because the target variable is categorical, it requires a nonlinear transformation. But the basic principle of how the input variables are related to each other in constructing a model is still a linear-based model. And we also have learned distance-based model. An example of that in this course is k-nearest neighbor, and it is by far the most intuitive supervised learning model that we have learned. And you also learned tree-based model, and decision trees is a good example of that. And you know that there are several different algorithms under decision trees. Decision and regression tree, or C4.5 or C5.0, different algorithms, but the basic principle of, or the basic architecture of decision trees remain the same. And these are so-called tree-based model. And you also have learned shallow neural network model in the previous week. And these are those neural network model that are fully connected and have a few hidden layers. So these are the so-called shallow neural network model. And the deep neural network model we haven't learned, but is relevant to the discussion today. So as you can see, the models are somehow sorted in the amount of complexity that is involved in the calculations. Distance-based model is intuitive, but it could take a lot of memories to conduct the computation because it's memory-based, and the data set can be of a high dimension, can include hundreds of variables, whereas linear models cannot typically take that many of input variables. So it's roughly sorted in the order of model complexity. Now, what I would like to discuss today about the big picture of supervised models is to show a trend of how they compare when faced with different situations, with different levels of problem complexity, and possibly with different sides of data. So I'm gonna do it here in the new slides. Okay, so let me put the 5 models that I discussed in the previous slides. So we have linear-based model. We have the distance-based model, which is a k-nearest neighbor. We have the tree-based model, and we have the neural network, and we have the deep neural network model. And if I were to use dash line for linear model and dash dot line for tree-based model, sort of tilde line for tree-based model, double line. Let's see, let me do that again. Double line for shallow neural network model, and plus symbol for deep neural network model. And let's compare these models based on one factor. Here is the problem complexity. Model performance. Okay, I would like to discuss how the performance of the 5 types of models would change when facing problems of different complexity. So as on the x-axis, as you go to the right model, and problem complexity is increasing, and on the y-axis, the higher you go, the better the model performs, meaning smaller error or smaller accuracy, or higher accuracy, smaller error. Okay. So as you probably would suspect, let's take the linear model as the first example. When the problem is less complex, when the problem is straightforward, and in this case, the data set is typically not large, but the larger the better. For simpler problems with a lot of data, with a large-sized data set, the linear model will be very good for these situations. So it could even perform better than the more complex models, such as neural network model or shallow neural network model or deep neural network model. So let's use these two as benchmark here for simpler problems. And the difference between these two types of models may not be as dramatic, but to separate the lines and to make the trend clear, I had to separate them out enough. So to reiterate, for simpler problems, and when you have an adequate size of the data set, linear models will perform quite well, as well as probably the distance-based model and the tree-based model. And the performances of these models may not differ by that much visually. They should be similar, but to show that the linear model will be the ideal choice, in this case, I put it on the top. Now, as you go to a problem of a medium complexity, the need for more data also go up, and you tend to have a larger data set in order to deal with the problem, and the number of variables or number of features available or needed from this data set also would increase. Now, in this case, as you have more variables, and when you train the data, it puts more burden on the model, and a lot of times you need some kind of capability to deal with nonlinearity. Some nonlinear ways of using the input variables in the data set to deal with nonlinear outcomes. So in this case, a linear model will suffer quite a bit. So this is a linear model, and in this case, decision trees will have quite a kind of a clear advantage, because decision trees, by cutting the planes in different ways, it deals with nonlinear relationships quite well, flexibly in a medium level complexity problem. So I put it here. This is the I'm sorry, I should have put the decision trees here. So the decision trees, here is the tilde line, and linear model will perform somewhat inferior, and so why don't I make the linear model a straight line? That will reduce the confusion here. And distance-based model, when faced with more complex problems, the reliability of the model may reduce, although it could still perform well. So it's somewhere close to the linear models here. And in this situation, the shallow neural network model will start to show some advantage here, because its nonlinear modeling capability will start to become effective in capturing the nonlinear relationships between the target and the input. So you kind of see an inverse of order here. Where does the deep learning neural network model stand in these two cases, it's hard to say. Deep neural network model is really capable. It's somewhat inappropriate to apply a deep neural network model to a very simple problem. It's like killing a chicken with a bull knife. It's sort of a overkill here. So I would rather not put deep learning model in this territory. But from here, its performance may be similar to maybe over and under the shallow network, just because a shallow neural network in this case would probably be sufficient. But as you go further toward more complex problems, such as computer vision, or some other more complex problems, let's see, natural language processing problems, translations, or detecting semantic relationships. In these problems, the deep neural network model will start to show its strong capabilities in extracting very abstract features. By abstract features, I mean features that are based on lower level features. So these are higher level features. Like in computer vision, to detect an eye, it needs to be able to detect the edges, the color, the contrast, and the finer details of the eyes and around the eye, around the eyeball, and even the eyelashes, and the color tone of the skin around the ear. None of the other models will be even will not come close to even being able to solve that. So all of the other models will kind of suffer, and it's hard to rank them. It's just more of a lumped together. And the reliability and capability of the shallow neural network model here will be uncertain. It's hard to say. Maybe in some cases it could do a better job, but in other cases it will not. So when I connect the dots here, the linear models will tend to decrease along the line here. So let's see, and so this is a linear model, and let me change this to, so this is a linear model. This initially is a distance-based model, and the distance-based model performance should be similar to the linear model as you increase, and it doesn't mean that its performance will be definitely even worse than the linear model, but it should be similar. And the tree-based model, when faced with the medium complexity problems, will tend to have some advantage, but overall it will keep decreasing as you have more complex models, as you have more complex problems. But the shallow neural network model will start to do better here, and it may not flatten too much, but will decrease a little bit here, and it could fluctuate. And finally, the deep neural network model will prevail, as long as you feed the model with sufficient data set, it will prevail, especially to these kind of problems and many other problems that involve a large set of input variables. So this is kind of the big picture. Simpler linear-based models, its performance will tend to decrease as you increase the complexity of the problem. But the deep learning models, those models with more complex architecture, will tend to hold its strength or even increase the performance as you have better complexities, as long as you feed large data sets to the model. All right, so that is the big picture I would like to talk about. And next, let me move on to model evaluations. So there are some quite interesting discussions to do here. All right, as a rule of thumb, when you compare models, we rely on some kind of criteria or metric of the errors that are committed by the model. And in evaluating the models, I can't emphasize enough that that you should focus on under two-way cross-validation, you should focus on the validation errors on the validation set, not on the training set, because for obvious reasons, you don't want to select a model that's badly overfitting, and you would select an overfit model if you focus on the training set. So this part, I hope, is crystal clear. For estimation problems, because the target is more numeric, and we call them interval type of variable here, there won't be a list of discrete labels, and all the values of the target value here, the target variable here, the interval variable, can be compared on a numeric and on a range of values. So the difference in the prediction versus the outcome, the actual value of y, would be y minus y hat. Y hat is the predicted or the estimated value. And this error provides a measure of how off the prediction or the or the estimation is from the actual value of y. And this provides a means to quantify the overall error of the model. And because there is direction here, it can be positive or negative, and because the objective is to accurately estimate the value regardless of positive or negative error. So in calculating an unbiased measure of error for the model, we need to take the square of the difference on every observation, on every row of the data. Calculate the difference and take the square, and then calculate the overall mean, which is adjusted by the number of parameters that P is the number of parameters that you include to penalize those super complex models and to favor simpler model that have adequate performance. This is how the adjusted R squared is calculated in regression models. And by using this notation, you have a measure of mean square error or average square error. The two are quite similar. And right, so regardless of which one you choose, this is the formula to calculate that measure. And inside SAS Enterprise Miner, when you select this MSE or ASE, this is the formula that is being used. And under a two-way cross validation, twofold cross validation, you have a training. Error is a thing that the model tries to minimize. If you have the training set performance of various models, this is model versions. If you have a training set line and you also have the validation set line, you should choose the model that minimizes the error term on the validation set performance, and disregard the training set performance as long as you have the divergent two lines. And this is the model to choose. Alright, so this is for the estimation tasks. Okay, a special note here, because multiple regression is particularly well suited for estimation tasks, and in the week of regression, the R squared, its scientific term is coefficient of determination. R squared formula. R squared by itself is not a very good measure or criteria for selecting the best model, because R squared will tend to increase if you keep adding the input variables. If you increase the inputs, you tend to increase the R squared. So you could potentially increase the R squared of the training set to 100%, if you keep adding square terms or nonlinear terms. So this is not a very good measure to select the best model. The mean square error by itself, even with the training set alone, without using cross-validation, it is a better measure to select a better model, because this model has a penalizing factor P, which measures the complexity of the regression model. If you have a very complex model by keeping a lot of inputs in it, its error term, its numerator will decrease. But by increasing a lot of the inputs or parameters in the model, the numerator will also tend to decrease. So the MSE is not moving monotonically as you increase the complexity of the model. So that's why MSE includes both the biases term, which is the error, the overall error, and the variance term. The numerator is actually incorporating the variance of the model. So overall, MSE is not moving monotonically, even if you have a super complex model. But here it's a sort of it's more of a academic discussion of comparing R squared versus MSE. Whereas R squared does not penalize the complexity of the model. MSE does have the capability to penalize more complex models and favor simpler models as long as they have equal errors by the model. And in this sense, MSE is similar to adjusted R squared, where by adjusted R squared, it takes the calculation of R squared, but it penalizes the for the complex models. However, here it doesn't mean that MSE is fully capable to select models that are not overfitting. That's not correct. By using MSE alone without using cross-validation, the model still tend to be overfit as you increase the complexity, even though it does have a capability to differentiate super complex models from those that are not super complex. But the boundary that it draws between overfitting and underfitting, or overfitting an optimal model, does not optimize for the amount of overfitting in the model. So that's why you still need a cross-validation mechanism, even if you are using mean square error as the criteria. Now, for classifications, by similar token, you will have the cross-validation mechanism, and you will have the overfitting chart, assuming that you have two partitions, the training and the validation set. So those things will remain similar. In this case, you will have a different metric, error metric, or error criteria, a normal or a traditional error criteria for a model developed for classification task would be the misclassification error, which is the amount of correct hit divided by the total number of observations. This is the proportion of correct classification. Proportion of correct classification. Perhaps in classic problems, this metric would be sufficient. However, in a lot of modern business problems where classification tasks is useful, using misclassification rate or misclassification error is not sufficient for reasons of decision making and decision cost. And this is why we'll introduce a few new concepts here. So based on the result of classification, there are those that are correctly classified and those that are incorrectly classified. So there is positive hit and negative hit. However, it is not entirely the same when you correctly classify a positive case and when you correctly classify a negative case, assuming that the positive and negative are the labels of the target variable. For instance, churn. In the problem of churn, the label, the outcome of interest is churners, is when churn equal 1, when a customer churned. And whereas the negative outcome, non-churner, when churn is equal 0, is when the customer decides to stay with the firm, and this is not of the primary interest to the firm. The firm would defer any actions if they are confident that the customer will not churn. Right? So in this case, there's a secondary outcome. In the case of binary classification, and they are not of equal importance here. So that's why we introduced the 4 concepts. We have the traditional error rate, the proportion of misclassifications, but we also have when the algorithm makes an incorrect classification, there are 2 types of errors. There are false positive and false negative. And by leveraging these, by leveraging the differences and the importance of these 2 different errors, one may adjust the weight of the errors, and one can improve the performance of the model, not in the sense of the absolute error rate, but the decision gain. The return of decisions. So that's what I'm going to talk about. So now, instead of having correct and incorrect classification, we also have the difference between primary and secondary outcomes. So now we have a 2x2 confusion matrix here. If we have true and false on both ways, and suppose that we have the columns representing the classification from the model, and the rows, these are classification outcome. But the rows are referring to the outcomes, the actual outcomes. Classifications do not have to be the same as the outcomes because there are misclassifications. When the outcome is true and when the classification also makes a true judgment, it is called a true positive. It's a positive case, it's true, and it's the primary outcome. Primary outcome is the true label. When the classification algorithm determines it's also should be a positive case, it is a correct classification and it's a true positive. When the outcome is false, it's a secondary outcome, and the classification correctly determines it's a secondary outcome. It should be false. It should have a false, or it should have a negative. So maybe it's better to label these as positive and negative, where positive means the primary outcome and negative means a secondary outcome, such as positive means churner, negative means non-churner. Customer didn't churn. And true positive is when the customer is going to churn, and the model determines it's likely going to churn. And when the outcome is negative and the classification algorithm determines it should be classified as negative, as a non-churner, this situation is called, the outcome is called true negative. It's a negative case which is correctly classified by the algorithm. So off diagonal line include two true outcomes, two true result, true positive and true negative. Now let's talk about the diagonal. When the case is a churner, but the algorithm incorrectly determined it's a negative case, it will be denoted as false negative. It's a positive case that's classified as negative. It's called false negative. Why is it called false negative, not false positive? Because the false is describing the decision here. The decision of the model is negative, but it's incorrect. So it's a false negative call. It's actually a positive case. So as you see, if the columns, if the headers are denoting the classification result, classification labels, then the false or the true is describing that column outcome. So naturally here it will be false positive, because even though it's a positive classification, it's actually a negative outcome. So it's false positive. Now we will work with this confusion matrix to discuss a few examples and to really understand what these means and how important are they. In the hands-on tutorial, in the PDF tutorial, in demonstrating model evaluation, it uses a data set called adult, and it is classifying the risk, or it's classifying the income bracket, higher or lower income. It's a binary target of individuals of certain group, and there are 10 there are 9 input variables. So let's talk about false positive and false negative. This confusion matrix is the matrix that I draw. It's similar. The headers or the columns are the predicted or classified outcomes, and the rows are the actual outcomes, and one would denote a primary outcome of the problem. So you can think of one as higher income, because banks are more interested in higher income earners. So higher income earners will take a value of 1. Or if they are predicted as having higher income, they will have a classified label of 1. Okay, now, so as I said, off diagonal cells denote the true outcomes of the prediction. When the classified label as well as the actual outcome is 1, it's true positive case. Higher income earners are classified as higher income earners. When the classified label is 0 and the actual outcome is 0, these are true negatives, which means lower income earners are correctly classified as lower income earners. but on the diagonal. False positive is when an actual low-income earners is incorrectly predicted or classified as high-income earners. And here, false negative means it's an incorrect negative classification. An actual high-income earner is incorrectly classified as low-income earner and classified to have a label of 0. And in this table, there are one more column and one more row. The column calculates the row totals. It calculates the total number of actual negatives on the first row because they all share, despite the different classifications. This column has a classification of negatives, and they are true. This column has a classification of positive but are incorrect. But both of these share the same actual outcome label, which is a secondary outcome, which is low earners. So the row sum would be the total number of negative earners or lower earners. And the second row sum is the total number of actual high earners. The added row calculates the column total, and these are the cumulative predicted number. The first column has a classification of 0, even though the top one is the true negative and true low earners, but the bottom one is false low earners. They are actually high earners, but the total here, the two cells will share the same classification label. So the column total would be the total number of predicted negatives, and the second column is the total number of predicted positives. And if you add the row sum together, these are the total number of cases inside the data set, which will be equal to, if you were to add the two column sums together, they will also equal the total number of cases, typically denoted as n, the total sample size. So the column sums will add to a number which is the same as when you add the two row sums together. Now, how is that useful here? Let's look at the data set, the actual results of the data set. By using a model trained on misclassification rate, which means, let's suppose that this is a decision tree model, and this model has the lowest misclassification rate, which means that it makes the least amount of errors when predicting labels, right? If there were equal number of high earners and low earners in the data set, this measure would be quite unbiased because it doesn't discriminate between positive and negative cases or primary and secondary outcomes. However, this is not the case. Remember that in the confusion table, in the confusion matrix, the row sums are the number of actual cases of the two labels. So here the numbers are conform to conventional wisdom. In the typical group of people, there are always smaller number of high earners than the number of low earners, right? So this row is low earners with a label of 0. And the total number of low earners is close to 20,000. But the number of high earners is only close to 6,000. It's 1 to 3. 1 to 3 or 1 to 4. Close to 1 to 4, but more than 1 to 3. So what does this mean? There are fewer high earners in the data set than low earners, and by using a non-discriminating misclassification rate on both outcomes, the model actually makes a biased determination in terms of the influence of the misclassification rate on different outcomes. To be specific, the model makes 18,000, close to 18,000 true negatives and close to 3,400 true positives. But the models commit these two types of errors with different numbers. The model makes 819 false positives, because this is the positive label. This is a negative or secondary outcome label. 819 false positives. These people are classified as having higher income, but they are actually low income earners. So the classification algorithm, the decision tree model here, it commits this many of the false positive errors. It also makes 2,500, more than 2,500 false negative errors, where these people are predicted to have lower income, but they are actually higher income. And you may wonder why it makes more false negative mistakes than false positive mistakes. The simple reason, or let's see, a simple description, which may not be totally accurate, but simple explanation would be that there are simply more negative cases in the original data set. There are more low earners in the population than high earners. So on average, an algorithm will tend to make more classifications of negative or the low income earners than positive earners. So it tends to make more mistakes on the in the sense of the absolute number of mistakes. It will tend to make more mistakes on the false negative cases than the false positive cases, but it doesn't necessarily means that the likelihood of committing a false positive error is lower than committing a false negative error. You would need to calculate the proportions here. So that's what we're going to do in the next slides. So the overall error rate is the misclassification rate here. And if you break it down to the 4 cells of the confusion matrix, it's the 2 errors that it makes, the false positive and false negative, because these are the 2 errors. The other 2, the off-diagonal cells, are the correct classifications, and they are these. So the errors here are in the model, or in the equation. The numerator includes the 2 types of errors, and the denominator simply calculates the total, which is the row sums or the column sums all together, which is the total number of sample size, right? So the overall error rate is the number of errors divided by the number of cases in the data set, and this is a non-discriminating error rate classification, which may not be appropriate or may not be unbiased when you consider the different types of errors. And now let's break it down to two types of error rate. Both of these are the error rate because they are false proportions. Proportion of false positive are those false positive errors divided by all positive predictions, regardless of whether or not it's true or false positives. So the denominator here would correspond to the column sum of the second column, of the column that is positive classification. So let's go back to the previous slide to confirm. False positive plus true positive. Here, false positive and true positive. That means the addition of them together is the column sum, which is the column sum of the column denoted by the positive classification. Right? So column sum of label 1. And the proportion of false negatives would be the number of false negative errors divided by the column sum of the 0 column. Let me go back 2 slides. It would be the true negative plus false negative is the column sum of the column with 0 classification label. So now you have two types of errors. Errors of false positive, proportion of false positive error, and proportion of false negative error. And these two reflect different aspect of the overall error rate. With a typical model, when you have a certain level of overall error rate, you would almost always have one of these error rate to be better than the error rate, overall error rate, but the other error to be worse than the overall error rate. And these two would almost never go in the same direction. As you increase and commit more proportion of false positive errors, you tend to commit fewer false negative errors. And vice versa, when you commit fewer or lower false positive error rate, you tend to commit a higher false negative rate error rate. So these two are almost never compromisable together. You may have a balanced portfolio. You have a fairly low false positive and false negative error, and in that case you will tend to have a lower overall error rate. But the question is, why does it matter here? Now it matters because business is not really the same as simply, correct and incorrect label in computing. In businesses, in certain cases, positive outcomes are more consequential than negative outcomes, and in some other cases, negative outcomes are more important or more consequential than positive outcomes. And here is what we're going to discuss in the next slide. Now this slide puts a number in and calculates the rate by using the example in the PDF demonstration, in the PDF tutorial. While the model commits an overall error rate of 0.13, that's slightly higher than 10% error rate. it misclassifies close to 13.5% of the outcomes. It does have a false positive rate or false positive proportion of 19.3%, but have a false negative rate of 12.3%. So you see that the model, even though the overall error rate is 13.5%, it makes a lower false negative rate, which means it tends less likely to incorrectly classify a higher income earner to low income earner. Which means that the negative classification, the classification into lower income earners, is less likely if the person is an actual higher income earner. So even though in an earlier table we see that the number of false negative is quite large, it's 2,400 something. It's a large number as compared to the number of false positive. It's actually less likely as compared to the overall error rate. It's less likely to commit a false negative error, but it's more likely to commit a false positive error because its false positive rate is higher. What is a false positive rate? A false positive case is when a lower income earner is incorrectly classified as a high income earner, hence false positive. It's predicted to have a label of 1, whereas actually the person is a lower income earner. So this percentage is higher than the overall error rate. The model is more likely to classify a lower income earner to a higher income earner. It's more likely to classify a low income earner as a high income earner. But is this good or bad? Depends on how this model, or depends on what the purpose is for using the model. If the model is used for loan approval, then bad news. Why? Because as compared to even though the overall error rate might be okay, the model is let me change the color here. The model is 86.5, close to 86.5% correct. It tends to have a higher likelihood than the average. It tends to have a higher likelihood of false positive. So it is more likely to mistake a low income earners as a high income earner. That means it is more likely to falsely or incorrectly approve a loan. Of low income case, where if correctly detected as low income earner, the company should not have approved this person's loan, because lower income is associated with higher likelihood of credit default, of loan default, right? So an increased risk of misapproval of low-income earners' loan application is bad for the business. All right, now, given that, example of income classification and loan approval, let's look at other situations. Now, in the case of loan applications, which error, false positive versus false negative, which error is more consequential? Meaning, if you would make a choice between these two errors, which one leads to loss of more money, or which one leads to the earning of less money? In this case, it will be the false positive, because when the algorithm makes a false positive classification, it leads to incorrect approval of the loan application of low-income earners, which leads to a higher likelihood of loan default. Whereas if the algorithm commits a false negative error, it will reject a loan application because algorithm determined that this person is low income, is negative outcome, is a low income earner, whereas in fact the person is higher income earner. So the company lost a business. However, losing one loan application and the resulting potential income from that one application is far less than the default amount of the loan if the loan is default because of low income. So out of one error, false positive error is more consequential than false negative error per error based. Now let's take a look at this example, which is more severe or more consequential in the decision making of sending direct mail solicitations for donation. So let's take a look at the decisions here. The primary outcome of one would be to classify or to detect that somebody is a donor. And the negative outcome would be to determine that somebody is a non-donor. So when you commit a false positive error, the algorithm mistakenly determined that this person is likely a donor, whereas in fact this person is a non-donor. So under the classification of a donor, the company will send a solicitation to solicit donation, but in fact the company will not get the donation because the person actually is a non-donor. In contrast, in the case of false negative, the algorithm determines that the person will be likely a non-donor. It's negative label or secondary outcome, which is non-donor. Algorithm determine this person is not a donor, and company will follow the recommendation to not send a mail. But since it's a false negative case, the person actually would be a donor if he or she received a mail, but unfortunately the company did not send a mail in the first place, so the person would, for sure not donate due to no solicitation. So in this case, in a direct mail solicitation case, which error, if you were to compare case by case, which error is more severe, more consequential? Now, in this case, you would have to calculate the cost and benefit. In the case of false positive, algorithm determined that the person would likely be a donor will send a mail which costs perhaps less than $1. But the company will not get anything in return because in the false positive case, the person is actually a non-donor. The benefit will likely be $0. So that is in the case of false positive. But in the case of false negative, in the case of false negative, because algorithm determined that the person will be a non-donor, the cost will be 0 because the company, by following the classification outcome, by following the classification result, the company will not send a mail. By not sending a mail, there will be no benefit. There will be no benefit here. However, there is potential benefit of a large donation here. It could be, to the magnitude of 100 or something, or maybe even in $20. In the case of false negative, the algorithm mistakenly predicted a donor to be a non-donor and decided and suggests that the company did not send a mail solicitation. However, making this kind of mistake will lose the company a potential donation of 100 by not sending a mail. So in this case, the error of false negative is more consequential. It leads to lost potential revenue for the company. I hope this makes sense. And now let's look at the third example here. Let me clear these out. Okay, now the case is, what's more severe in the decision making of detecting cancer, or which is similar to a fire alarm? In medical diagnosis as well as the fire alarm, there is a false positive kind of alarm versus a false negative. Which one is more consequential? I'll let you think about it, and I'll talk about it in a few seconds. Now, in the case of a medical diagnosis or fire alarm, in fact, false negative would be more severe, and here's why. The primary case here would be referring to fire or disease. And so in this case, the primary outcome is not a desirable outcome. When the algorithm commits a false positive error, it is a false alarm. It alarms the patient on the possibility of the disease or the fire and calls for action. So the cost here would be inconvenience in the case of fire, because everybody have to leave the building for fighters to diagnose the building. And in the case of medical disease, it is alarming the patient to do a follow-up check. The cost may be in the tens or maybe in the tens or up to a couple hundred for the diagnosis. But the potential benefit is to rule out the disease, because if the case is a false positive, then the follow-up test or the firefighter's check-in will rule out the case that this is actually a fire or disease. So there's no fire and disease. The false positive will be corrected by a second chance. However, in the case of false negative, the algorithm determined that there is nothing to there's nothing to be alarmed. There's nothing to there's no danger. It's a negative classification, whereas in fact there might be or there's in fact a fire or a disease, but it's falsely or incorrectly classified as negative, as no fire or no disease. In this case, people continue being in the building and have a far higher likelihood of death due to the fire being out of control, or a false negative in the medical case will lead to a loss of opportunity for the patient to catch the disease in early stage, and it would be too late for the patient to seek for medical help when the disease, especially cancer, in late stage. So in this case, false negative leads to missed opportunity of diagnosing the cancer, which leads to cancer being in late stage and higher likelihood of death. And because death is more costly than other inconveniences and cost of a couple $100, so in this case, false negative error would be more severe. And if you compare the second with the third scenario, the determination that the false negative error is more severe or more consequential is regardless of whether or not the primary outcome is a desirable or non-desirable outcome. In the second scenario, the primary outcome is a donor and it's a desirable outcome, whereas in the third scenario, fire or disease is a non-desirable outcome. However, the determination that the false negative decision or the false negative error is more consequential is the same determination here. All right, I hope this exercise is interesting, and normally we would hold this as in-class discussion, but with the asynchronous video, I can't do that. Hopefully, but I hope that you'll go through the same amount of consideration in your mind, and you have followed this discussion and conduct the same type of exercise in your mind. Your homework for this week, homework 7, I believe, will deal with a specific scenario, somewhat different from the scenarios here, but the principle will remain the same. With that scenario, you will determine which error is more severe, and you will elaborate why. And so with the discussion of two types of errors, and they make different senses in different business scenarios, one can continue to optimize the model based on decision weights, and the decision weights can be set based on a determination of which type of error is more consequential than the other type of error, like we discussed previously. So in the case of loan approval, or the lending case based on people's income levels, because a false positive is more expensive here due to the loss of income from a defaulted loan, the algorithm should try to minimize false positive more so than to minimize false negative. So after optimization step, by adjusting the decision weights, the algorithm should instead be less likely to commit a false positive, as versus the previous case when the decision weights are not set, and when the two types of errors are equalized by default, the model tended to have a higher likelihood of committing false positive error than false negative error. Now, after weight adjustment, the model should be far less likely to commit a false positive error, which is more consequential. So let's see how to do that. In a decision cost matrix, one would denote or input values for different levels of cost and benefit. Of course, cost is negative plus benefit. You will assign values of the sum of benefit minus cost to different decision outcomes, and those weights will be incorporated in the calculation of the decision outcome of the different algorithms. And in this case, because false positive is more expensive, more consequential than false negative, the decision weight, the benefit minus cost value of the false positive is set to be twice as big as false negative, to apply more weights on, or to apply more penalty on false positive errors. And after doing that, let's see what will happen. So, this is the same confusion matrix with different outcomes. This is the decision tree model with adjusted cost weight. And here's the difference. What used to be close to 900 false positive case is, I guess, reduced to 305, and what used to be close to 2,400 false negative cases increased to over 3,000. And it's a dramatic increase in the absolute sense in the number of false negative cases, and the percentage-wise, it's a dramatic decrease of false positive cases. And as a result, you will see that the false, the total number of false predictions, including false positive and false negative on the diagonal line, the total number of false predictions increased from the previous decision tree model to the current decision tree model. But does it make sense dollar wise? If you were to compare the two, the new model makes 10% likelihood of false positive, and because false positive errors is more consequential, it's drastically reduced from the earlier close to 20% likelihood. But at the same time, the proportion of false negative increased from previously 12% to 15%, and perhaps increased to be larger than the overall error rate. But even with this heightened error rate, the overall gain from the classification model is expected to increase. And here is the difference. So this is how the decision weights are configured by inputting into the project decision weights. In the lending case, for true positive case, if the algorithm correctly classifies a higher income earner to be a higher income earner, the expected revenue is from the loan application is $300. In terms of the cost, it will be minus 300, which means positive 300 revenues. But keep in mind that when you specify cost or benefit, it is one measure that lumps the cost and benefit together. In the case of false negative, there will be no cost, because even if the person is higher income earner, the loan is disapproved. The loan is rejected. When the loan is rejected, there is no expected cost, or there is no real cost and benefit from this decision. But in the case of false positive, a low income earner is approved the loan. On average, the loan default amount is $500. So the burden of cost to the company per false positive case is $500. As you can see, the expected cost of false positive from expected revenue of true positive is higher. So with this change of configuration, the result becomes that this is in terms of cost. So negative cost means positive revenues. It's positive savings or positive revenues. With the previous model, which treats the two types of errors equally, the revenue is 617,000. But with the optimized decision weights, the revenue is increased by close to 5 or 6%. So it's a significant difference even for a small business, for a small bank. Right. All of these difference is because of the changing because of the change of the ratio between the cost and benefit of true positive versus the false positive versus the true positive. So if you follow the PDF tutorial if you follow the PDF tutorial, you will go through the same exercise and you will get the same result of the improved decision outcome. All right, so make sure that you follow the PDF tutorials to do the exercise. Also, in the previous semester's demonstration, the model evaluation is also included. Okay, I'd like to discuss a little bit about deep neural networks and how neural networks model is able to accomplish fantastic results in terms of computer visions. You know, nowadays, deep learning models are very popular because they are able to recognize very complex visual cues and can correctly classify many objects. And here is a brief account of how they are able to recognize facial features and correctly recognize a human as versus an animal. So in the deep neural network model, the first layer is the input layer, and in fact, the first layer is the raw value of the photo. You know, for instance, the photo of this female's face. The input layer here would include the RGB scheme value of every pixel of this picture, and flattened to be a large vector of values for one picture. You know, so the input layer could be potentially huge. You have the different color schemes, and you have many pixels. You know, for an easy picture of 640 by 640, you have more than something inputs here, so it's potentially huge. And the first layer here, will try to, based on these pixels and the colors, will try to figure out the edges, straight edges of the color, the hairline, the forehead, and the chins, the faces, the eyebrows, but the straight lines, and ears. The reason that the first layer will try to do this is because of the architecture of this layer, and this kind of network is commonly known as CNN, convolutional neural network. The C is referring to conv layers, and by the architecture of the conv layers, it's based on the raw picture pixels, it's best able to recognize the straight lines, the straight edges, and highly contrasted areas, two planes. So it's able to pick up those easier or lower level features. But as you add another layer to this lower feature layer, it's then able to combine different angled features to have curved lines, So it's not in one step that the model is going to recognize the eyes, the noses, and and even the hairs that don't go in one direction but kind of as a lump, but you do have hairlines. It's not in one step, but takes several steps. And in general, you tend to have a larger first layer and somewhat narrower second layer, but fatter. It's actually, there's a depth in it, but the depth is shallower in the first hidden layer, but deeper in the second layer. And as it goes deeper, it will have a much shorter layer, but much deeper hidden layer. It will imitate somewhat like a triangle shape, but now you have a 3-dimension here. As you go deeper into the hidden layers, you will be more likely to recognize high level, more complex combinations of the features, and by the end it's able to combine those features and determine that, oh, this picture is more like a human. It possesses those features that are typical in human pictures, in human faces, than those in dog faces or in other kind of object like chair or tables. So that is a few comments about deep learning networks and team projects, because we're not using team formats in final projects. I won't talk about this. Model deployment. So once you have, by now you have learned different supervised learning models, and you know how to compare them by using model comparison node. You also have learned advanced model evaluation topics by differentiating two types of errors, the false positive, false negative errors, and you know how to set decision weights differently in order to encourage the model to emphasize one type of error than the other and improve the decision outcome of the models. Now, once you have a best model, how do you predict new sample cases or new cases or out of sample cases? Those cases are not even in the test set. Test set is technically part of the training set, but you are purposefully hiding the target values of test set or validation set from the training of the model in order to do the cross-validation mechanism. But out of sample data are not even in your train or validation set. It's a score set. The notation of out of sample set in SAS is score set or score data, and it is in a separate data set, and you would need to import it to be able to deploy the model and to make predictions on a new set. And here I'm going to quickly demonstrate how to do model deployment here. And there are two alternatives. You can use a score code, or you can use a score node here, or you can also choose to use an export or save data set node. Save data. So there are two ways. Option 1 uses codes, and option 2 uses a node, and both way works equally well, and so so choose according to your preference. If you want to do a bit of coding, then choose the SAS code. Otherwise, choose the save data node. And in the next part of the video, I'm going to demonstrate how to do it. Okay, start. Alright, I have the project set up here. As you can see, this is the same project I demonstrated last week, in the previous video, and it's using the restart. Alright, so here's the demonstration for deployment. I have opened the project. This is the same project that I demonstrated in the previous video in the last week. It's the donation dataset. It is using the PV-A97NK dataset. So assuming that I have trained my best model here, and the best model here turns out to be neural network. It's slightly better performing than the decision trees. So what do I do after I have compared the models and have chosen the best model? The best model will come out of this model comparison node. So I should follow the scoring node after the model comparison node. So here, let me zoom in to make it larger here. Now I am suppose that I'm ready to score the model. I need to create two things. I need to bring in a score dataset, and I need to use a score node. So first of all, the score dataset. A score dataset is a score data source that I need to import to the SAS project here before I can, before I can bring the node to the path, to the diagram. And so now I need to create another data source here. And you should, before you do this, you need to make sure that you have downloaded the score dataset, which is different from the train dataset. It doesn't have the target variable column in it. It doesn't even have the column. Not that it doesn't have the value of the target value. It doesn't even have the column. Here it doesn't have the donor or donation target variable column in it. So that's a score data source. So to create a data source, I can right click here, or I can do the file new. I'm going to right click data source and create new data source. And by the way, this demonstration follows the tutorial of the PDF tutorial, the one about scoring dataset that is shown on the screen. All right. So I'm going to magnify this one. I'm going to do this, and I discover that I can avoid, I can avoid distangling the item that I click from the item that's shown on the cursor. In the last video, there is a disconnection between them. Here, I discover how to avoid those situations. I need to bring the magnifier into the region where it's magnified to avoid that situation. Okay, so I will create a data source in the same way that I created a data source for the train. I need to look for the data, and here the data that you should look for is the score data set, and suppose that you have one. And now I'm using a fake PVA fake score data set. It is not exactly a true score data set, but it can fulfill the purpose here. So I would choose that, and I might have zoomed out of the region, so I have to redo this. Okay, magnify. Oh, it's too big. The table is too big. Okay, click OK, and let me redo this again. So next, I'm going to configure this table And instead of going to the advanced, let me do it one by one. Use the basic. So here, for a score data set, I should not be able to see the target. So in the real score data set, you won't have these target. So, so here to imitate the score data set, I would have to reject the target B, which is a target variable. And also I will reject this because in the training set I do not have. I also rejected the target B. By rejecting both of these variables, it is imitating a score data set where it's actually not exactly. Also, in configuring your score data set, you want to make sure that the rows and levels besides the target variable, you want to make sure that the rows and levels are exactly the same as you did in the training set. So I'm going to skip this step because it's very tedious. But when doing the project, you want to make sure they have the same configuration. Otherwise, SAS will give you a problem in the process of the scoring. Okay, confirm the number of cases. And score data set tend to be small because this is a fake. This is exactly the training set actually, but I'm using it as a fake score set to demonstrate the process. Number of rows tend to be small in the score set. And it's a score set. This is very critical. You want to make sure that you change the row here. You want to make sure that you change the row here. Because it's a score set, you want to explicitly change it to score. Do not skip this step, otherwise you'll run into a problem. Okay, after that you confirm the levels and number of variables, levels, rows of data set of variables in the data set, and confirm. Now that you have a new score data set here, to score this data set, you want to drag that to the diagram, and you can put it parallel in vertical manner to your model comparison, because both of these nodes would need to feed into the next node, which is the score node. In the score node should be in utility. Score code export. Maybe it's in assess. It's in assess. So bring the score node into the diagram and rearrange the diagram. It's the score node that is used to apply the trained model, the best model that you select, on the score dataset. So you need to link the model comparison node and the score dataset together to the score node, and you can mostly okay, let's do this. You can mostly accept the defaults, the default setting of the score dataset, but it also allows you to specify some of the other options if you want. If you do have a test set, you can choose to score the test set. I don't have a test set here. And you can choose to generate the SAS code of the entire score process and optimization process. Here, I don't. You can turn off the reporting of the graphical of the results graph, and I'm going to accept all the defaults here. So after that, you can run this to score. Now, because it's fake data set, because I didn't compare and make sure all the variable rows and levels are exactly the same, I may run into problem here. So don't be surprised when you see a problem, see an error in your score process. It indicates that there are something that you have to check and make sure those issues are cleared. It takes some time for the score process to complete. Oh, great. So the score process actually finished successfully. That means the score data, even though it's a fake score data set, the specifications of the variables are correct and the same as the training set. Now let's take a quick look at the results here. So let's do the magnifier here. Where is it? Okay. And target is a binary variable. And let's take a look at whether or not there is important outcomes here. Important results. Class variable summary. And I do see here that there is, so in addition to the classification, in terms of the label of the scoring, you have a positive or negative donor classification. Besides that, the model internally also produced a probability of the target. The prediction of the class or the classification of the label is based on the probability that a case is predicted to be a donor. So this probability column is it's a product of the model scoring process, and it is an interval variable, so it shows the the statistics of this variable. It does have a median of close to 50%, so half and half. Half of the cases were predicted to be donors and half non-donors. And whereas target B no is when the outcome is predicted to be a non-donor with a label of 0, and predicted to be a donor where the label is 1. So that's all the results here. Not many important things. So, and let's also take a look at the exported data set here, and we should expect it to at least see two new columns. One is the probability of being a donor, and the other is the actual classified label of the case. So exported data set of the score node. So we look at the score, and let's browse. And all of these should be the input and as well as the imputed variables. And beginning here, these are the product of, or some byproduct of the scoring process. And the two columns actually have more than expected, because the target variable is a binary. Because the target variable is a binary variable, it has two different labels. So algorithm will output the likelihood of predicting both labels separately. But you know that the probability of two labels should add up to 1. So for the same case, the likelihood of predicting a label of 1 is smaller than 0.5, and it will be predicted to be a label of 0, which is non-donor. And the likelihood of predicting 0, 0.616, should should be 1 minus the likelihood of predicting the label of 1. So if you add them two together, it should be close to, it should be 1, and they conform the result. And if you go further to the right, you will see the prediction for the target here. And the prediction to the target, I said for the first case, it will predict a label of 0, which is non-donor. And here you also see the same two columns. So the scored data set, the output from the scored data set actually includes multiple columns of the results, but they are somewhat redundant here. Whenever the predicted probability is over 0.5, it will it will predict that the outcome is 1. But when the probability for the target is below 0.5, it will predict the outcome, the label, as 0. So you can confirm these results. 1 whenever it's over 0.5, 0 whenever it's below 0.5. Okay, so the predicted columns are confirmed in the export data set of score. So now I'm ready to export the scored data set, which is different from the score data set. Score data set provides the inputs of the new cases, whereas scored data set will provide those inputs as well as the outcome, the predicted results of those cases. Now, as I said, there are two approaches. There's an approach with coding, and I will demonstrate that first, and afterwards I'll demonstrate how to use a SAS node as an alternative to save the data, to save the scored data set. Now, to do the SAS code, you'll find under utility there's a SAS code, and bring that to the diagram and connect the score. Connects the score node to SAS code. And for SAS code, the only thing that you need to do is do a little bit programming, and you need to open this. This is called Code Editor. Click the ellipse. It will take a little bit time for it to come up, because it's trying to locate the function, a deep function in the SAS Enterprise Miner, the codes function, the interface to access the codes deep inside the software. So it takes a little bit time here. And now we have it. I need to bring the magnifier again. I always accidentally close it, so I always have to reopen it again. And here, the only thing you need to change is the training code here. So let me magnify this portion. So that's the training code. And I need to talk a little bit about the SAS syntax here. As you start typing, this is kind of a part of the IDE, integrated development environment. It will color code the different codes that the different keywords that you type in. The first line, as according to the page 7-14 of the PDF tutorial, it's a data statement, and followed by something dot something else. The portion before dot is the library, and because your library is different from what the tutorial on the PDF shows, so you should use your own library name. If you need to check the library, go out of this window and to check what your library is. I remember that my library name is mylib, so type mylib, and then the portion after the dot should not be altered. You should copy exactly, so type exactly the name of the exported score data. This portion should not be changed. I mean, the portion after the dot should not be changed. It's difficult to highlight the exact portion. Exported score data, and this is the keyword for the exported data of the score node. And don't forget this semicolon here. After that, go to the next line and type 2 spaces. The exact spaces don't matter. The indentation here is not mandatory, but it helps organize the codes. And the first line of code, what it does is it creates it created this new data set in SAS. The data statement is creating new data set. And the second line of code is to copy an existing data set. And for this existing data set, it's in the memory, it's not in the library. So you need to, you will type the exact same name of the dataset in the tutorial. It's EM Enterprise Miner underscore import score. It's the dataset behind the score code. And don't forget the semicolon. And then the last statement is run. So this will tell it to run the block of code. Okay, so that is it. Double check the names are correct. EM import score. And this is the data set that will be exported and will become the name of the data set that you will find in Windows Exploratory. Now I am ready to run. Before I close this window, I'll make sure that you save and close it. And now I am ready to run this score, the SAS code to export the data set. After it runs successfully, I should be able to find a SAS data file in the library, in the folder that the library points to. MyLib is pointing to a location under the place where I normally keep all the other SAS data sets and other projects. So, and it it does run successfully, so I'm going to open the File Explorer. No, File. Let me open it from my computer or this PC. I should be able to find under the D drive SAS Enterprise Miner, I should be able to find the exported scored data. EM exported scored data. EM exported scored data has a date of April 5th, 6 o'clock. It's right now. So confirm that this data set is the data set that's exported by using the SAS code. All these are not because they have a different time. Last year or more than 1 year. And because I'm going to use the other method to export the data set, I'm going to temporarily move these to another folder because they will have the similar names, and I don't want to overwrite all of these data files. So everything that starts from EM, I will move it to the new folder. And okay, now let's come back. And this is method 1. The alternative method is by using a save data node. So let me bring the save data node parallel to the SAS code. You understand that this is the alternative method of exporting data sets. All right, in configuring the save data node, let's do a few settings here. You can specify the library name, and in this case I'm going to specify the same library name here, and it's MyLib. And alternatively, you can specify a direct path to any directory that of your choice. You don't even have to have a library available there. Output data, which do you want to output all rows? Yes, it will output all the data set, including the train, validation, and score data set. Or you can specify a specific row of the data set, other than train. If I don't want train, I don't want validation, I don't have test set, so changing this will not matter. Transaction, I don't have transaction row of set, so changing this will not make any change. But score data set, I do want to export and save the score data set, so I confirm this is yes. While the other train, I don't even have the validation. Even though I have the validation partition, it's technically still under the train row of data source. So make sure you select no for train. Then anything other than the score data set will not be exported. And if I run this, I should expect to see an additional data set appearing in this same library. So let me sort by the date. This score data is the data that I exported previously by using the SAS code. And after the save data node successfully runs, I would expect to see an additional data set here, additional score data. There you go. The save. No, I thought I did not want. Okay. Even though there is no validate data set, it will output this one, and it I don't expect to see this, but it does. But anyway, I don't expect to use this. Let's see if it changes after it runs successfully. Alright, it runs, and let's check the data sets again. I do see 2 additional data sets, but only the score data is what I need. I can safely remove the validate data. So 2 ways to extract the scored data set here, and both ways are successful, and they should be the same, even though their size is different. If they may contain different numbers of the input variables, but you know what you really care is the the prediction results. All right, I hope you enjoyed this video, and see you later.